Hello everyone, I'm Janith from Department of Civil and Environmental Engineering in Seoul National University, and today I'll be taking you through my research to identify the behavior of a sudden influx of soluble pollutants in rainwater for drinking, in short RFD systems, and the remedial strategy that we are going to propose during operations to remove such pollutants. So I'll be taking you through a brief introduction giving you the water problems that currently exist and the rainwater harvesting and the design and operations of it, and then to the objectives of the research, followed by our experimental setup and the results and discussion, which would be finally concluded with the take-home message. So to kick off with, let's have a look at the water problems and how rainwater is connected to water problems. As you already know, there's a scarcity of water in the world, and there are about 785 million people. They do not have access to safe water. And about every 2 minutes, a child dies due to water-related issues such as diarrhea. And women in most of the developing countries, they have to travel about 200 million hours collectively to collect drinking water. So from these statistics, we clearly highlighted that there's a need to find a high quality water source, and that water source has been identified as rainwater because it has a short pollutant inflow route. So because of its short pollutant inflow route, there's a small pollution in rainwater, which makes it very easy and economical to convert into potable water. So let's have a look at the rainwater harvesting systems, a typical rainwater harvesting system. And we know that rainwater is pure, and the collection and the storage of rainwater is called rainwater harvesting. And as you can see, a typical rainwater harvesting system consists of a roof, and a first flush, a storage tank, a filter, and a point of use disinfection system. And in developing countries, there's a new development to create multiple tank systems as rainwater harvesting systems, especially for community-based rainwater for drinking systems, because it creates better particulate water quality. However, whether it's multiple tank or a single tank system, if there's a prolonged die period, because almost all the dust and all the pesticides, herbicides, and all these pollutants, they get deposited onto the roof surface, and after a dry period, with the initial rainfall, all these pollutants get washed up and come as a sudden influx into the first flush and the storage tank. And of course, if there's a first flush present in the system, it can remove about 60 to 70% of the pollutant influx. But in most of the developing countries, a first flush is not provided. So now we have clearly established that the storage tank itself is responsible for managing this sudden influx of pollutants. And while the particles can settle with time and then we can easily drain it out, soluble contaminants remain within the system. So because of it, there's a need to identify their behavior within the rainwater harvesting system. And we have to identify whether the design and the operations of the storage tank can handle this influx of soluble pollutants. So let's move into the research and the research gaps. As for the designs, me and Professor Muyong Han from my academic advisor, we have investigated the effect of inlet and outlet configurations on water quality for both particulate matter and for soluble contaminants, and it is presented in this journal article. So the research gap is in the operations part. And we have identified that previous studies only focus on the particulate matter and the drain operation to how we can remove the particulate matter from the tank system. But we haven't found any studies on soluble pollutants or any article concerning how the overflow can be utilized to improve the water quality of harvested rainwater. So in light of it, we have identified the following objectives for our research: to investigate the effect of number of tanks on transport of conservative pollutants during water storage, and to identify how we can use the overflow and drain operations to manage this conservative pollutant in rainwater harvesting systems. And finally, by investigating the first objective and the second objective, we want to suggest some design and operational recommendations to achieve better water quality. So to start off with, let me explain you our research and our experimental design a bit. So we are going to simulate two tank systems. Firstly, at individual households, let's take a school for an example, we can design the rainwater harvesting tank to cater only to the demand imposed by the children or like the teachers in the school system. So it would have a tank volume of, let's say, V. And now if we design this school to provide water for the entire community, it would have multiple tank system. And let's say the tank volume would be 2V and 3V. So in the case of individual tank system, what we are going to simulate is like basically two cases. One case would be we are going to allow the water to overflow about 50% of the tank volume, because overflow is extra water. It is not going to reduce the amount of water that we have stored within the tank. So we can have a higher outflow. So the conservative pollutant that we are going to use and inject as a sudden pulse input would be salt, because it is a common pollutant in coastal areas such as Sri Lanka. And as for the drain function, we are going to drain only 0.25, that means 25% of the volume of the tank, and even lesser, like 12.5% of the tank, because when you're draining, you don't know whether the rainfall event is sufficient to fill the tank up to the top level. So because of it, we have to be conservative with the amount of water that we are going to drain. So all this time, while simulating these scenarios, the outflow would be 0. So we are going to simulate the scenario where the water is being stored. And as for the multiple tank system, we are going to simulate the same two scenarios, the overflow and also the drain, while keeping the outflow as 0. So moving on, these are the tank dimensions and the scenarios we have simulated. The tank dimension is as follows, and we have used a scaled down tank, and the scaling factor is about 10. And while we scaled it down, we have maintained geometric and hydraulic similarity to a real scale tank. So the hydraulic aspects of the research, or the hydraulic aspects of an actual rainwater harvesting tank, is kept. And these are the scenarios that we have simulated. Scenario A would be just filling the tank, and scenario B would be where the overflow scenario is simulated. And scenario C is basically like a stepped rainfall, where the first rainfall will fill the tank half, the first tank half, and then the second rainfall would completely fill the tank. And scenario D is where we are going to drain 0.125, 12.5% of the tank volume and 25% of the tank volume, and then finally the tank volume will be filled to the top. So let's now go into the results. Now, with the increasing number of tanks, as you can see here, from 1 tank system to 3 tank system to 2 tank system to 3 tank system, the conductivity has reduced. And that is because of the dilution, because now we are having V volume being upgraded as 3 times the volume. So because of the effects of dilution, the conductivity has gone low. So the pollutant concentration has reduced. And if you look at the mass distribution among tanks for 1 tank system and 2 tank system and 3 tank systems, you can see that for 2 tank system, with low flow rates, more contaminants tend to remain in the first tank itself. Whereas in high flow rates, more contaminants tend to go to the second tank, which is because more advective force forcing the contaminants and forcing the water flow to reach the second tank very fast. And if you look at the third tank system, you can see that first and second tank holds the majority of it, and as expected, when the flow rate increase, there's a higher percentage of the pollutant or like the soil concentration is retained in the second tank. More or less, for both flow rates, the final concentration in the third tank or the final tank remain almost the same, which is also beneficial in terms of rainwater harvesting because we need a consistent water quality. As for the effects of overflow, as you can see, with higher number of tanks, low mass is transported with overflow. For one tank system, about 40 to 50% of the pollutant is being carried out with overflow, whereas in two tank system, it has been reduced to about 25%. And for three tank system, it has further reduced to about 10%. And with the changing flow rates, low mass transportation with overflow has been observed. You can see that with high flow rates, not much has been taken out with the water flow for one tank system. I think it's because of high advective force, there's a better mixing. So because of the mixing, the overflow water is more diluted. I mean, the concentration gets more diluted with the overflow, and then the diluted concentration goes out. So it's the same with two tank and three tank system as well. Now let's move into the drain operation. As you can clearly see, when compared to the overflow operation, drain operation is not that effective to remove a soluble contaminant. And with high number of tanks, again, the mass transported with the drain has reduced because easily the pollutant gets carried on to the second tank and the third tank, vice versa. And with high flow rates, we have increased mass transportation with drain water. Even though it's not significant, there's a marginal increase. And that is probably because like with much advective force now, it is being flushed out, and better mixing forcing the water to get flushed out, forcing the pollutant to get flushed out with the drain water. And with high drain mass in the last tank reduce. That means with higher amount of pollutants that we drain, lesser amount of pollutants gets stored in the last tank, which is obvious because we are draining much of the pollutants outside in the first tank and second tank itself. So in conclusion, we have clearly demonstrated that multiple tank community-based systems are better in terms of water quality. So for a school, it is better to convert it into a community-based multiple tank water system rather than a single individual tank system that caters only to the students or like only to the community within the school itself. And also we have demonstrated that overflow is effective for one tank system, but it might not be effective to multiple tank systems because when it is a multiple tank system, more pollutant tend to get stored in the last tank. And we have clearly demonstrated that draining is not effective when compared with the overflow operations. As for the suggestions for operation and design recommendations, it can be said that it is better to allow water to overflow in one tank system and to use a flow diverter for multiple tank systems to prevent overflow. And by considering the particulate water quality also, we can suggest that the drain valve operation of the first tank should be done until the clear water comes out following the first rainfall event after dry season. And during dry season, no draining is actually necessary. And with that, I conclude my presentation. Thank you so much for listening, and if you have any questions, I would be happy to answer.